Hello everyone, it's April 22nd. Alright, so yesterday I didn't do this, but I also didn't check the solution. I did submit because I just need to keep the streak going. But I gave this a little bit more thought, these hints, and I think it makes sense. It makes sense. So if we can get today done fast, I'll definitely go back to this. The hints is actually pretty good, right? And all three are very useful. All three are very useful. So hopefully we are able to get back at it today. But we're gonna start. Okay, so that is definitely a sign. That is definitely a sign that we will do it because it's an easy problem. So we get it done. That's a count again. Every single day is count, 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 count. So we'll get this done and then we will get the other one as well. 1 to n is grouped according to the sum of its digits. The number of groups that have the largest size. They're grouped according to the digit sum. So there are 4 groups with 2. So we have to go through them, right? Calculate each one, put them in a group of the digit sum, and we just count. Okay. Yeah, this is very simple. Actually have to do the 23rd. Maybe not as simple as you thought, though. Int digit sum. How would you calculate digit sum? Mod 10. Mod 10. Mod 10 divided equal to 10. Mod 10 divided equal to 10, and then we'll return rest. Okay. So we need a map. A counter, right? For I equal to, we start from where? 1. ds equal to digit sum I, and then counter I plus plus. Once we're done, we need to count. Okay, so int res is 0, int max size is 0, and for const, no, I think it's auto const key value. Okay. And then what do? We say if value is larger than max size, and max size is equal to v, rest equal to 1. Else, if v is equal to max size, then rest plus plus. And at the end, we'll return rest. Counter with the key be in the digit sum. answer? 13. My bad. Was a typo. Then why don't you just do, this? Oh, there's a faster way. Oh, there is a faster way. Yes, because the largest is 4 nines. 36. Yep. Counter 36, so it is 37. And then for this, we just need to say V. Oh, we can sort. Nah, I think that should be fine. It doesn't matter. There we go. So that is the solution. Yeah, it didn't occur to me why you use a map for this. Absolutely not necessary. Okay, so yeah, we got this one done. Now the real thing starts. Okay, so here's my epiphany yesterday from reading the hints. So the hints say we will find strictly increasing. Okay, strictly increasing array that satisfied the requirement. So again, we all use this this example 5 and 3. So max value, right, is equal to, actually 3 is not a good example. Let's go to 9. Okay, max value is 9. Okay, so if the first, so we have 1, 2, 3, 4, 5. If the first one is 1, okay, and we are dealing with strictly increasing, so the second one has to be 2, 3, 4, all the way to 9, right? So it's a second one if it's 2, right? And then we can ask how many are starting with 2. So you will have 2, third one, no, we can have 4, right? And we can have 8. So 2, 4, 8 is one possibility, right? But for 2, 4, 8, and then we'll couple with 1, then this is the combination coming. Basically, we do 2, 4, 8, and we can put them anywhere we want them to be put, right? So that's essentially a 1, 2, 3, 4 choose 3, right? It's a 4 choose 3. 4 choose 3 is equal to 3, right? So we have 3 different ways to put them. No, we have 2, 4, 8, 2, 4, 8, 2, 4, 8, right? And then for each combination, we're just filling the remainder to the right with the same value. So this will be 8, this will be 4, this will be 2. And that's it, right? So that's why we need to find the total number of strictly increasing. But of course, if it's 2, right, and you say, okay, if it's 2, then it has to be 2, 4, 8. It's actually you can also do 2, 8, 2, 2, 6, right? You can do 2, 6. You can do 2, 8. You can do all of them. So you have different. So we have 2, 4, 8, and we actually can can try it, right? We'll have 2, 4, 8. Actually, if we really want to do it, let's go a little bit smaller so we can really trial run this, right? So if it's 1, then this can be 2, right? If it's 2, then we start with 2. How many do we have? And not only how many do we have, but also we need its size as well. So 2, we can do 4, and 4, nothing, right? But 2, we also can do 6, right? We can do 6, and that's nothing. Well, that's all start from 2. And now we can also say start from 3. Start from 3, oh, also 2 can be by itself as well. So we have to do 2 by itself. So 2, yeah, let's do it this way. I'll have 1, 2, 2, 4, 2, 6, 3, 3, 6, and 4, 5, 6. That's all starting from 1, right? And then starting from 2, I already did. I know 2 can be by itself. 2 can do 2, 4, 2 can do 2, 6, and then we have 3. Like, we all have that mapped out already, right? We have it mapped out already. Therefore, what I want to know is, starting from a number, give me the number of how should I say it? We start from a number, so we say 1, right? How many we have? If we have 2, how many we have? If we have 3, that's 3, how many we have? Right? How many different ways do we have? And 4, right? So I can produce this. Basically, this is a dpij. Okay, dpij is starting from value I, right? Starting from value I, with j, with length of the array, right? With length of array as j. What is the total number of different choices? Right, this is what we're looking for. And this can be computed, because starting from max value, right? If max value is 6, okay? If max value is 6, so dp 6 1 is equal to 1, because it's always 1, but you can now do 2 because that's 1 is the most, right? Okay, so now we have dp5 also 1 is equal to 1, and dp4 1 is equal to 1. Now we have dp3. Okay, so 6 divided by 3 is 2, so we can do a most 2, right? We can do a most 2. Now if we do a most 2, we can say dp3 1, that's only 1, because 1 is always 1. Now dp3 2, which is length is 2. So if its length is 2, then we need to say the first one is 3 and the second one, right? So the second one is, you can multiply by 2. So basically this, so dp3 2, right, is equal to, so we set a 3, and then we go for the next one, which is dp6, right? 3 times 2, and then we can also try 3 times 3, but that's out. So basically. That gives you only 1, right? That's only 1. And now dp2, 2, 1, yeah, 1 is always 1, dp2, 2. So basically we start with 2, and then we're looking for dp4, that's 1. And we're looking for dp6, that's 1. So that gives you 2. And dp2, 3, 6 divided by 2, it is 3. But I don't think we can get 3. Huh. Can you get 3? No, you cannot. But the division is 3. So if it's a 3, then it has to be 2, 4, and 8. So you can't get to 3. So what we can do is we start with 2, right? And then we do 2, 2, 4, which is 2. So we add 4. And then we will keep going to 8. Then we add 8 if it's possible. If it's not, then yeah, we just don't have we don't have a dp3. Okay. So now the last one is dp1. And we don't really need dp1 because we just don't need it. Okay, so this is what we have, right? So now we're gonna start from 1. Or 1, of course, 1 can go by itself, right? So 1 go by itself. Okay, so we say dp starting from 1. So dp starting from 1. So dp1, 1, hold on. So dp1, 1 is definitely 1. dp1, 2. So 1 with 2. So 1, 2, 3, 4, 5. Just basically you add them together, right? So dp 2, 1. So 2, 1 is 1, 2, 3, 4, 5. That's equal to 5. And then dp 1, 3, length is 3, and then we're hitting length 5. Length 3, and then dp length 4, and then dp length 5. I don't know, we just put it out there. So when we do length 2, we just go through. So 1, we say, okay, I go 2. Right, okay, times 2. And then that give you 1. Actually, let's simulate the whole thing. Let's simulate the whole thing. Right, so we have 2 right now. It's 2, and then we look for dp2, 1. That gives you 1, and then it's 2, and then you look for dp2, 2. Right, dp2, is 2, which means this we have 2. dp2, 3, it doesn't have, so we drop. Now we're looking for 3. Okay, 3. So we're looking for dp3, 1 is 1, and dp3, 2 is 1. So this is what becomes 3. dp3, 3 doesn't exist. Now dp4, 1, dp5, 1, dp6, 1. Right, so it's 1, 2, 3, 4, 5. So that's how you get to 5. And once you get to 5, this will get to 3. And then these are just, we can set to 0. Great. We can set these to 0, like you just don't consider them, right? So that's dp1. Okay, so with this in mind, now we are going to use the now we are going to use the combination. So dp1 right? So length is 1, and additional is basically 0. There's nothing. So we'll do for choose 0. I think choose 0 is always 1, right? For choose, yeah, for choose 0. So this will give you 1. So for 1 as 1, let's give you 1. And now we have 2. Length is 2. So basically this is for choose 1, right? As 4. But I have 5 different possibilities. So that's 20. And this is 3. So 4 choose 2. 4 choose 2 is 6. And we have 3 of them. 3 times 6 is 18. Okay, that's that. So basically, once you find it out, you can do it. And now we have 2 at a start, which I believe is the same thing. Somebody asked me if I can share some documents because they think I added a function. But I'm pretty sure I am not the one who added the function. Yep. We have an Indian team helping us. So they just started working now. So the code base basic is 24/7. And this is the same, right? Because it's just starting with this. So with the length, right? With the length is deterministic, right? 1 is always 1. 2 is always 20. Oh, that's not true. That is not true. That is not true. Holy crap. This can be, oh, I see. Okay. So anyway, so this is 1, right? This is 1, but this is not. This is just 4, this is 8, right? This is 8. So this is also 1. This is 4. And these are 1, 1, 1. So the total is 1 plus 20 plus 18. That's 39. 40. 48. 49. 53. 54. 55. 56. So 5, 6. I expect it to be 56. Boom! That's 56. Okay. I think we are ready to implement. Yeah, I think we are ready to implement. So the DP size, how many rows? Will be max value rows. How many columns? It will be max volume columns, right? The maximum, actually that's not true. The columns are the maximum we can support is the count is n. So we have n columns, but not all of them will be filled. Okay. All right, let's do this. Let's do this. All right, so let's write this one first. So this is a solution, right? LeetCode 2338. This is a solution inspired by the hints. We will use dp, we'll define dp such that dpij is equal to the number of strictly increasing array starting with number I and with the size being j. Then for each number, right? For each starting number, right? For each starting number, if there, actually, let's use an example of n equal to 5, max value equal to 6. If the first number is 1, there are two ways to put two more numbers in the array. Right, 2 3 2 4 2 6. Actually no, it's 5 different ways. Two 4 2 6 3 6. Where are 5 come from? Oh wait, hold on. It's 3. Yeah, total is 3. Yeah. So 2 4 2 6 and 3 6. Right. For each array, there are 4 choose 2 number of ways to organize the two numbers. For each such organization, we can create an array, an ideal array, by filling the empty space with the same value immediately to its left. For example, if we go with 1 underscore 2 underscore 4 underscore, then the ideal array is 1 1 2 2 4 4. If we go with 1 2 4 this, then the ideal array is 1 1 1 2 4 4. Alright, so now is the time to find. So we'll define factor int, no, that's an array of array, at least for now. So I say dp max value rows n columns. Oh, that's not how it's defined, right? All right, let's keep going. That's not how you define this. I'll do vector. That's how you define. We have to probably go n+1, right? And then this is probably also +1 as well. So that is the DP table, right? And we are going to do populated. Oh, but the population itself, we will go right to left, right? We'll go right to left, and we'll start from the biggest value, right? So we start from the biggest value, and then we'll say how many we can do, right? How many we can do, and then we adjust. So okay. So for I int I shall equal to max value, I larger equal to 1, I minus minus. Okay, that's the first one. And for j need to start with the number count. So for j equal to 1, j smaller equal to n, and j plus plus. Okay. So when j is equal to 1, right, it will always be 1, right? And then we say j equal to 2, and then we need to have the previous actually that is not right. I think what we need to do is to realize if, okay, so let's do this. If I times 2 is larger than n, no, larger than max value, right? If it's larger than max value, then we only have 1. So in that case, we can set dpi 1 is equal to 1. That's it. Else, this is where the fun starts. Else is I times 2 is larger or equal to max value. So at least we have something to go with it. So when that happens, what we do is we will try different, right? We'll multiply by starting from 2, okay? And then we'll say how much is 1, how much is, and then we multiply by 3, multiply by 4, until the multiplication is, all right, so in that case, we can say for int, it's not j, but because it's for the multiplication, right? This is for this multiplication, and then we will go through the other thing, right? So int k equal to 2, right? And k times I need to smaller or equal to max value, k plus plus. Okay. Then what? For each k, I have I times k, right? Now we can do dp that, right? We can dp that. And we say for int j equal to 1. I think we have a better idea, because dp I1 will always equal to 1. So I don't even need this, right? I don't even need this. This will always be equal to 1. And then I try to do this, right? So j equal to 1. Actually, I've done 1 already, so j equal to 2. what's the end condition is j need to smaller equal to n, and dp I times k j minus 1 is larger than 0 j plus plus. Okay, so when that happens, we'll say dpi j plus equal to dpi times k j minus 1, right? Because j, I say, okay, so we'll do dpi 2, so I times this, but I need to do my j minus 1, like what that is. And then we go, we done, and j will move on to the next one, just like longer size, right? Longer size. And if I do longer size, I need to make sure that the underlying one is larger than 0. Otherwise, we cannot do, right? If it's 0, that means it does not exist. And then we'll just exit. That the first one that does not exist will exit. And now I'll try k equal to 3. I'll try k equal to 4 until k times I is too big. So yeah, so this will give me the dp value, right? So this will give me the dp value expected. Oh, here. All right, so this is the populated dp. Say populate dp. All right, so now dp is populated. We can have, now we're gonna do interest. We need a function. I have to call it private. Comb n choose k, right? N choose k and mod. Right, compute n choose k with mod. Right, we have to mod this, yeah. So n choose k is this n minus 1, we do a k times, right? So int, actually we do a long numerator, right, equal to 1, and then we say for int I equal to 0, I smaller than k, because we do k times, right? So we do n and n minus 1. So like it's, if k is 2, we do n and n minus 1. Right? K is 2 and n minus 1. So we say numerator so equal to numerator times n minus I and the whole thing mod k mod. Okay, so yeah, multiply, well, mod, and then we'll do that. Okay, so that's that. Ooh, then we have a division. I'm not sure if division will work in this case. Huh. Mod inverse. Hey, really? That's how it's done? Yeah, we have to do a factorial. We'll do a factorial. Pre-compute factorial. Pre-compute factorial. So we only need to compute it once. That is actually not bad. Okay, well, pre-compute factorial. And modulo exponentiation. Power. Binary exponentiation. A modulo inverse. Compute a modulo multiplicative inverse using Fermat's little theorem. Holy shit. What the hell is this? Modulo inverse. Power n and modulo minus 2. If p is prime, then a minus 1 and a to the p minus 2 mod p has the same modulo. What? Dude, you're killing me. Oh wow, I need to copy and paste this entire thing. Holy. Oh. Damn. Alright, we need to copy this entire thing. That's how you do the combinatorial. Oof. Oof. What is this Fermat's little theorem? Yeah, I am a little bit skeptical of what the hell this is, but if p is a prime, then for any integer a, the number ap minus a is an integer multiple of p, which means this and this, which means if it goes to minus 1 power, and this will be minus 1. And that is the thing that's used. But this is minus 2. Why minus 2? Oh, because it's 1. Minus 1 is 0. So if we were to go negative 1, it have to be minus 2. Oh, you gotta be kidding me. Miller-Rabin primarily test. I remember doing something like this very early on. I think I have a GitHub stuff for this. The Miller-Rabin primary test. Oh, Pierre de Fermat. That is some. Okay, so that's how you do it. Oh, Lord. Okay. I thought. All right, so basically we need a vector of int, right? And we'll call it it's factorial, right? It's factorial. So this is fact, okay? But I need to get a length. How many? How many do you think? Well, the most factorial is n, and n cannot be longer than 10 to the 4th. So you can either do it here, just give it a large number. Or, yeah, I want to do it, just give a large number, 10 to the 4th, 1, 2, 3, 4. That's not that bad, okay? So this is a, hold on, it doesn't work that way. Oh, really? Oh, man, he still don't know how C++ works, right? Yeah, I don't want to do with this one, though. Ah, but it's fine. We'll pre-compute somewhere else. So it's just a vector, right? And then we'll do... How do you pre-compute? Oh, we'll do void pre-compute factorial, right? And I'll need max, yes, max size, max n, okay? And then, oh, we also need a mod. So what we're gonna do is, you know, just times this, we'll mod, times, we'll mod, and put it in, and then put it in, and put it in, and then fact dot pushback 1. This is factorial 0. And then for int I equal to 1, I small equal to max, and I plus plus. Fact dot pushback fact dot size minus 1 is the last one multiplied by I, okay, and then the whole thing, well, I have to go long on this thing to make sure it's a long, right? So it's a long times, let's make this one a long as well, okay, and then we'll mod a long mod, right? And once we do all that, we'll turn back into an int. So basically the last one multiplied by this, okay, by I, and then we'll mod it, and then we'll push back, and then we'll just keep going, and until we're done. Alright, that's that. We'll do pre-compute. We'll do pre-compute factorial. Max and m mod. I do need a mod. Mod is 1, 2, 3, 4, 5, 6, 7, 8, 9. And we'll do, this is basically just mod. Alright, so we'll pre-compute. That's done. We also need power. So we'll say x raised to power of p with mod. Press this 1. And then we have a base, right? Base is equal to x. So basically, power, so while p is larger than 0, if p mod 2 is equal to 1, right? So when that happens, res equal to res times, we know times an x, right? We're gonna time a base, that without the actual base. So we'll times x, and then this thing will mod. And then we'll say, oh, actually not times x, I think it's times base, right, times base. And then base will equal to base times base, of course we'll mod, and p divided equal to 2. And we'll return res. Alright, this actually I'm not quite sure, so I need to do this. Yeah, it does make me think. Maybe put everything long is a better idea. If everything is long, we don't have to do all the conversion, and then we'll. You know what? I like this idea. Let's make everything long. Yeah, let's make this a long. This is a long. It should be fine, and then this shall be a long. Everything is long, then we just do fact this times I mod. Ha ba da da. Right, and then here is the same. We just get everybody long. Oh, what did you do? Right, everybody's long. I wonder if the call. So let's call this one also long. And need to be long. Okay, so that's power. I actually didn't even check power. Res. Base. It's fine. Base will not be longer than that. Well, p is larger than 0. If this res times base mod, otherwise base equal to base times base. Yeah, that's right. So we need a inverse int. No, let's do long. Okay, so this will be invert power. No, it's just inverse. All right, inverse. So long n. So compute long mod. Compute n to the -1 modulo mod using Fermat's little theorem. So we'll return power n to the mod -2. Which states that if for any integer a, if p is prime, then a to the p and a has the same modulo against p. Thus, a to the p -2 has the same modulo and a -1 has the same modulo against p. Power mod. Right, n to the power and do that. So that's inverse. So combinatorial. Yeah, long, and this is long. Everybody's long, and this is long and long. Compute n choose k, right? So n choose k, so numerator will be factorial k. Actually, no. N, right? Factorial n. Because n factorial divided by n minus k factorial and k factorial. Sorry, so when we say long, a numerator, a denominator, that is factorial n minus k times factorial k. And that shall mod, right? And I will return numerator times inverse denominator mod, and the whole thing need to mod. Alright, wait, this one I have to check. That's modulo inverse, yeah, numerator, modulo inverse times modulo inverse mod. This times this. So I think because it should be the same, right? It should be the same. Okay, so now we have a combination, right? We have combination. Then we can start saying for each one, right? Because I have dp, so we'll start from 1, then we'll do dp, no, 1 1 1 2 1 3, right? 1 1 1 2 1 1 1 2 1 3 up until a point where it's 0. Then we'll, okay, so for int again I equal to 1, I smaller than because start from 1 and then we all go all the way to maximum value, and dpi 1 is larger than 0. So once we hit something that's not, and that's the end. Okay, I plus plus. And for int j equal to, no, we have 1, j needs to smaller equal to n. Same thing, right? And dp basically ij need to be larger than 0, and the j plus plus. All right. So we have dp ij. So I need to rest will just plus that, right? Just plus that because now it's only 1. Essentially, we don't need to compute 1, right? So we can say res plus equal to 1. This is essentially handling. This is handling dpi1, which we basically don't need to handle because everybody's the same, right? Now we start from dp res plus 1. Mod, right? Now we start from 2, and res need to equal to int c is combinatorial n minus 1, right? N minus 1, that's c, n, choose k is j minus 1, and mod. Okay, and then we'll, coming back, we'll int this thing. That is a C. Oh, actually, no. Why are you in this thing? Let's continue dealing with long. Okay. So long is good. Long is good. Long is good. And then this is not long, so I need to get this one to long. Everybody else is long, right? So combinatorial I have, and then we need to divide this multiplied by the number of different arrays, which is dpij, right? This is dpij. So res shall equal to res plus, why you do res as int? I don't understand. Long, right? So times c times dpij, and dpij, why are you int? I don't know. I shall be long. Everyone shall be long. Okay, that's fine. And do I need to mod this one? I think we need to. Basically, dpij plus this. Okay. Mod. But everybody's long, so that's fine. Here's the same. C times this, because we have C different combinations for each one of them, right? And we have dpij, number of unique arrays. So we do that, we do a mod. And at the end, we'll return int res. All right, this is kind of the first iteration of this. I have very low, like I really do not know if, okay, what the hell happened? I really do not know if this one will work. And but we can put in here. It is significantly longer than the solution that we copy and paste yesterday. It looks solid. Let's try. See how it goes. Could have tested more. Memory limit. I wonder which one. It's definitely not this. This is fine. Memory limit. The only memory limit is DP. Okay, I agree. All right, the DP is pretty much not the best way. We need to shrink it. Right? We need to shrink it. How? So what's the longest basically you can get? Well, the longest you can get is, I don't know, 2. So divided by 2, that's pretty much the longest you can get. Okay, let's try just divided by 2. Max value divided by 2. That. So no, n divided by 2. And of course, it's longer than we don't even have to consider. There are two savings here. But I wanna stop right here. We are on the right trajectory. What we need to just to make the memory usage smaller. So we don't need all those columns. So the column I can divide by half, right? Yeah, the column definitely we can divide by half. And the column I can divide by half. The rows I can also divide by half. But let's do column divided by half first. So instead of n minus n, so I can do n divided by 2 plus 1. I don't know. Give it a shot. But for overflow, because this has to be smaller or equal to divided by 2. And this is also divided by 2. Oh, this one's correct. But we fail all of this. Shit. Oh, man. I think has to be plus 1. Why don't you just use a length? Right? I think I just use dp length. Well, we should make things a lot simpler, right? Smaller equal to, you know, dp dot size. And this we can say smaller than dp0 dot size. Or even better, we can say m equals dp dot size, n equal to dp0 dot size. Right, and here I just do m. Right, this is n, and this is m, and this is n. Oh, what? Plus 1 doesn't work? This is the max value. Is 5. Oh, I think it should be the max value divided by 2, not n divided by 2. It's max value divided by 2. Like 6 divided by 2 is 3. Yeah, the smallest is times 2 times 2. 2, 4, 8. That's the smallest. Right? Which means it's log. It should be log. Log 2. So it's max value log 2. How do I do log? std log 2. N plus 1 like this. Plus 2. There we go. Efficiency boost. Efficiency boost. The max length of an ideal array cannot exceed log 2 max value plus 2. Right, this is the scenario. Oh, yes. There's a scenario where the array starts with 1 and 2 and continue doubling until max value is reached. The length of strictly increasing we have the great text case, like 1 2 3 4 5 6. Oh, 1 2 3 4, right? 1 2 3 4. That is the maximum that we can do. All right, this one looks promising, and there should be some other efficiency boost. That's not bad. That is not bad. 54 and 54. This is from yesterday. Okay, yeah, there's a lot of efficiency boost, but this so far so good. Okay, so this is 54 millisecond. Yeah, which means we're in the right track. 54 millisecond, 54%. Good. See, I'm telling you, like, if I do this early in the day, then I get a lot more energy out of it. All right, that's pretty good, right? We got at least one iteration of the solution. So there are a few that I can think of. Maybe we don't need to do 2 rounds of run. Maybe 1 round is sufficient. We don't need to set up the entire n plus 1 row. No, max value plus 1 rows. Maybe it's possible to reduce that as well. So there are a couple of things, and it's also possible that we don't even need to use a 2D array. Maybe we can just build it on the go. But anyway, I think I'm gonna check the answer. This is good, right? This I'm happy. This is definitely a new trick. Never thought about it, but that's all right. Okay, that will be it for